Hello, Calculus. You'll be observing this class after class on Thursday, so that's the 17th. So we've been talking about the first derivative test, and then we ventured into some who-struck about the concave up and concave downward. So before we go headlong into the second derivative test, I want to talk about another portion of a curve that we haven't talked about yet, and we're going to need it. So we're going to talk about, well, we've already talked about concavity, so let's start. That'll be a good starting point. So back to concavity, and we talked about a positive concavity looking like that, and a negative concavity looking like that. Alright, so there's my little face to help you remember that. Alright, now what if the concavity changes signs as you're going across the graph of a function? So what if you have this going on and then this going on? So it starts with a concave up or a smile, and about right here it starts frowning or concave downing. And that is going from positive concavity to negative concavity. And that point of change there, right here, is called an inflection point. So get these in your notes, and I need to check up on your notes, so I'll do that tomorrow. Alright, now what if it went from negative concavity to positive concavity? You see there is an inflection point right there where it's going from a negative concavity to a positive concavity. So another inflection point. And these inflection points always exist between changes in concavity. Alright, so we're talking about also the second derivative is positive here, and the second derivative is negative here. The second derivative is negative here, and the second derivative is positive here. So that's an inflection point. So how would you find inflection points? Given a function, you would take the first derivative and then the second derivative and set it equal to 0. So you're going to see where it's neither a negative concavity or a positive concavity, and right in between the concavity is 0. So that will be indicative of an inflection point. There are other kinds of inflection points that we will meet in the next part of this discussion. So just put that on hold for a minute, and we'll just go on. And we're trying to aim toward the second derivative test. I never did title yesterday's video, so I guess it would be Introduction to the second derivative test. But today we're going to arrive the second derivative test. Alright, so let's see what that's about. Alright, and before I go into that, I do want to talk about the first derivative test. They're so related, so we will not leave the first derivative test in the dust. So, in fact, let's dust off our first derivative test and recall what it was about. It turns out if you have a function and you're looking at the first derivative, f prime, let's say that we have a point where the first derivative is 0. And again, the calculus is usually the easy part. Finding where the first derivative is 0 is sometimes more challenging than we would like for our algebra, but I guess that's good for us. And so you're going to take the first derivative and set it equal to 0, and say we found that the derivative is 0 at a certain point, and then we have found that the derivative to the left of that point is positive, to the right is negative. You'll recall from our previous discussion that this indicates that there must be a positive slope, then a zero slope, and then a negative slope. So this is indicating a max. And that reminds me, I should emphasize when I say the second derivative test and the first derivative test, what are we testing for? We are testing for relative max and min. So far we've seen that sort of test, and you haven't done those problems yet, but well, maybe you got to them today. If not, you will very soon. And then suppose we have another spot where the first derivative is 0, and just to the left it's negative, and to the right is positive. That means the slope is down, then the slope is 0, and then the slope is up. So positive, negative slope, zero slope. So that tells us that we have a local min. So that's the gist of the first derivative test. And now I'm going to discuss the second derivative test. And before I do that, there is one more case that I should go over with the first derivative. And what if it is not positive and negative, or negative and positive? Well, what else could it be? We'll say we have a 0 derivative and we test to the left, and say, for example, we get a positive derivative, and then we get a positive derivative to the right. What does that indicate when we're looking at first derivatives? Well, it means that we have a positive derivative, so it's going to be coming up. The slopes are going to be in this direction from lower left to upper right, and you can see the slopes along here would be, sketching in lightly the tangent lines, you can see their slopes are positive. Then I have to zero out at the top where it's going to have a flat tangent slope, but then it goes positive again. So then it goes like that. So that point right there is neither a max nor a min, and therefore not every critical point, every zero derivative is going to give you a local max and min. You have to test both sides. So I like to call that an uphill rest. That's just, you won't hear that normally. That's my little colloquialism there. So it's sort of like you're climbing uphill and you get a little rest here where it flattens out, and then you climb some more. So that's an uphill rest. So probably won't surprise you that if the first derivative is 0 at a point, but we get negative to the left and the negative to the right, we have a situation where we're sloping this way, 0, and then continue sloping negative. So notice all the tangent lines along here, except right here where it's 0, are still negative slopes. So let's call that a downhill rest. Did you ever notice? Sometimes walking downhill is harder than walking uphill, and you need a rest. So there's your downhill rest right there. So those are all the possibilities for finding left and right behavior from a 0 first derivative. All right. Now let's grow into the second derivative test. All right. Let me get a spot where I can write a little more above and below. So right here, again, this is looking at really both tests, but teaching the second derivative test. Well, let's look at a first again, f prime, and say we have a 0 here. Oh, another point, if you go back in, I just thought of back here where we're looking at these critical points where the first derivative is 0. I forgot at a critical point also a possibility instead of 0 is the derivative does not exist. So what would this slope look like? If it's positive to the left, the derivative does not exist here, and a negative to the right. Well, it would still be a local max, but it would like come up and have a sharp turn. So at that point, a sharp point, it would not have, it would be no derivative. So this is does not exist. That's what DNE I'm talking about. Does not exist. The derivative is not 0, or it's 0, or it does not exist. And here, this is also true. We could have a derivative that's 0 or does not exist. And again, we could have a sharp turn like that, and that would qualify. And let's look at, when we jump over here to the second derivative, we could have a 0 derivative or a does not exist derivative. And say we don't really care to look into what's happening to the left and what's happening to the right. It's a complicated or complex function. We don't feel like plugging in numbers. And so let's go from there to what's called the second derivative tests. Again, we're testing for the same thing. Is the point a max, relative or relative min? So it turns out that if at this point where the derivative is 0, first derivative is 0, actually for the second derivative we're not going to be allowed to do the do not exist first derivative, because if the first derivative is a sharp turn, say it's curving up and then it goes like that, right here it's a sharp point, we wouldn't be able to draw a tangent to that in order to find the slope of the derivative to get the second derivative. So in this case, we're not allowing the do not exist points. We're only talking about where the first derivative equals 0. So say at that point the second derivative, so you take the second derivative and whatever point we're at, it turns out that it gives you a positive second derivative. So what would that create? It creates a concave upward, which must be a local min. So sometimes it's a whole bunch easier to take the second derivative and see if it's positive or negative at a given point. So if it is positive at that same point where the first derivative is 0, then we have a local min. And if we had another situation where at the same point that the first derivative was 0, this time we'll say the second derivative is negative. That means we have a concave downward, so therefore we have a local max. Alright, and that's the basis of the second derivative. So let me shut this down. It's probably going long enough, and I hope I haven't gone over. If I did, I'll split that one up as well. Alright, so be back.